Hey everybody, it's Chad from Patriot Astro. I've had a lot of questions, mostly from new people in the hobby. In the last several months, we've had quite an explosion in the hobby of astrophotography and using telescopes in general. And there's a lot of questions that are fairly basic, just about the components and parts and what do I really need to get started. So what I want to do here is go through a single video that is going to introduce you to the components. I'm not going to go too deep. There may be a couple pieces where I go a little bit deeper than others, but for the most part, we're going to try to keep it as simple as possible in this single video, just to give you an overview. And more likely than not, a couple things will happen from there. One, you will need to get online and search some of the keywords that I use to learn a little bit more, as you're ready to do so. The second thing is I may have to come out with some additional videos to go a little bit deeper into some of the other topics. So hopefully this helps, and let's go ahead and get started. So first thing, as we start from the bottom up, we've got our tripod. It's going to be critical you get a sturdy tripod, right? Any movement whatsoever, any vibration, you name it, you're going to end up with a situation where your images, especially longer exposures, could just be throwaways, right? So a good sturdy tripod is going to be a must. You can even get vibration dampening pads for under the tripod legs if that helps. So just something to consider. So the tripod comes up and stops to about right here. Now from here up, we end up with the mount. Now this particular mount is a German equatorial mount. There are a couple different types you're going to find when you get into the hobby or start looking at telescopes. You're going to have alt-az, so altitude azimuth, or equatorial, EQ, right? German EQ, CEM, GEM, you name it. There's a couple of them out there. For astrophotography, you're going to prefer an equatorial mount. They're going to cost more money, but we're going to explain briefly here why you're going to want an equatorial mount. But let me go back to a basic example of an alt-az mount. And what I'm going to do for that is just pull out a camera tripod, a basic camera tripod. I've just got a DSLR sitting on probably the world's cheapest tripod here. And when we talk about alt-az tripods, you'll notice one thing is that the telescope or camera or whatever the imaging device is mounted directly on top for the most part. It's pretty centered, so we don't have any weight issues, balance issues, typically. The other thing you'll notice with alt-az is that the way it rotates is pretty logical. So beginners like this, you also have a situation where it's not just beginners, but it's also people for visual astronomy. It's very easy to move and target things. So what we have here is if I can rotate in this direction, this is our azimuth. So this goes from 0 at north all the way back around to almost 360, right? So 0 at north, east is at 90, south is at 180, and we can just simply rotate. The other axis of movement with an alt-az telescope, or mount rather, is altitude. So in this case, altitude, right? We start to go up, and this goes from 0 at horizontal on your horizon all the way up to 90 at zenith if I point straight up in the air, right? So this is obviously very easy to target, very easy to move. You have a couple challenges with this. Because the Earth rotates, the stars are going to go in an arc across the sky. Anything you're trying to image arcs across the sky. We've all seen this as we watch the moon arc across the sky. And it rotates around the celestial North Pole. So a couple challenges you end up with in that particular case is that in order for me to track this object, you're going to notice that I'm going to have to go and move on two axes all the time, right? So I'm going to have to be changing my azimuth and my altitude. Anytime I have to move on both axes, that's a second possibility for some sort of error that I'm going to run into. Mechanical error, different types of errors that are going to limit my exposure lengths. And there's even some other challenges beyond that. So let's jump away from this rickety old tripod pretty quickly. And let's get back to an equatorial mount. Now this is a Skywatcher EQ6R Pro. There's a lot of different ones that are out there. There's even some portable models. But what you'll notice right away is there's a couple different things. So one, we have an axis that is like this, right? It's going in this direction. So that particular axis is going to be aligned with the celestial North Pole. So by aligning that with the celestial North Pole, what that means is that one of our axes is going to be fixed on the rotation point of our night sky, right? So it makes it pretty easy. So what we can actually do here, if I release the clutch, is to just briefly show you. And of course the clutch is sticking, but you can see what I'm doing here is I'm able to rotate around that axis. So let's think about that for a minute. The night sky rotates on that axis. Now my mount, if properly aligned, also rotates on that axis. So what does that mean? That means once I have this telescope set up and pointing at an object, through the night, this mount only needs to track along a single axis. We're just gonna move at 15 degrees an hour, right? So the Earth, we got a circle of 360 degrees, 24 hours in a day. A degree every 4 minutes, or a 15 degrees an hour. It's just gonna sit and rotate mechanically, and that should be able to keep us in a pretty good place to take some great images, assuming a solid polar alignment. So for the most part, again, what do we have? With an equatorial mount, the ability to only move, hopefully, on a single axis for corrections through long exposures and through multiple exposures, right? So that makes life a lot easier. So that's one way that you can benefit from a German equatorial mount. Now the second axis here is going to rotate the top of the scope, and that's going to allow us to go in the other directions we need to go. So let's go back and talk about a couple different things you're going to run into though with an equatorial mount. There's a couple things to know. Most of these telescopes have a polar alignment tool built in. So the equatorial mounts, you'd take this cap off the back, you'd be able to look up through the shaft, and then there'll be a reticle that'll actually have some star map information. And based on an app, you can go look online and figure out where the celestial North Pole is in reference to Polaris. You can line that up and get a very precise alignment, because again, making sure that's aligned equatorially on the celestial North Pole is going to be critical to us moving on a single axis, which gets rid of a lot of our error, allows us to take much cleaner images and much longer duration images. Now another option here is to add a polar scope. So you'll notice on the front here I've got a camera, and this camera's only purpose on the front of the scope, and it's lined up right on the axis, right? The only purpose of that camera is to talk to a piece of software on my computer only at the beginning of the evening for me to do a polar alignment. So it takes me through a procedure. It can see the night sky, it sees Polaris, it has me do a couple things. I can do a video on this later, but it'll actually make sure that I'm extremely well polar aligned. Now, you can simply use what's built into your mount. You could go and get a polar scope to get maybe an easier, better alignment. There's also several software packages that'll allow you to use the cameras and everything else you're using already to properly align and do a polar alignment. So you have a lot of options there. I personally find that the PoleMaster camera works fantastic for me, so I couldn't imagine living without it. But again, there are other ways to do this, and there are ways to do it without an additional cost if you're just using what's built in. So we talked about with the Altaz the fact that the telescope itself is centered. You'll notice here, because of the angle we're at, the telescope is not centered, right? The telescope is up and to the back. And not only that, but with Altaz, I can move in any direction in the imaging portion of the unit, whether it's a camera or a telescope, stayed centered. So I didn't have any balance issues. It's a little bit different with an equatorial mount, right? Because now if I start to, again, move my telescope, you'll notice now I'm not centered, right? All of the weight of my cameras, my scope itself, they are not over the center. And because of that, we end up having to put counterweights. You have a counterweight bar, counterweights, and what you're gonna do is try to get this as balanced as possible. So you'd level it, you'd move your weights, make sure it's balanced so that it's not moving. You see mine is just sitting here. It's in perfect balance. And because we have that balance, now the motor does not have to work extra hard, right? If this was out of balance or I didn't have counterweights, it would be difficult for the motor to try to lift this telescope up, and then it would be fighting holding it up in the air when it was going down on the other side. right? So again, equatorial mounts, again, they get a little bit heavier because you have counterweights and you have to deal with that as well. Now, I didn't mention the axes on the equatorial mount. Remember, in alt-az, we had altitude and we had azimuth, right? The rotation on the horizon. With equatorial mounts, we have RA and dec, right? So right ascension and declination. So right ascension is that rotation piece where the telescope can kind of flip back and forth. That's your right ascension. Declination is your ability to rotate in this direction, right? So this way is this is your declination. If you don't memorize that, don't worry, someday you will, but it's not super important for the most part at the beginning, especially if you're going to automate most of your practices. So just something else to think about. Now, before I get off the mount portion here, whether you choose alt-az or equatorial, and again, for astrophotography, you want to go equatorial. The one other thing I do want to mention briefly here is that there is another challenge with alt-az mounts. So with an alt-az mount, and in this case, again, we'll just use our camera tripod. Everything in the night sky is rotating, assuming I'm pointing at the celestial North Pole and I'm properly aligned right now. Everything is going to rotate this way. And as an object rotates, it is going to maintain, right? It's going to rotate and maintain its position in the sky. So initially, if the object is oriented way on the horizon over here, pointing off to the right side of my telescope, it'll eventually get up high in the night sky and it'll be pointing upward. And then when it gets down, it's rotated, right? Because the whole night sky is rotated. Because my RA axis rotates the same way, my camera, my telescope is always in the same orientation. So I can take these long field images over time and the rotation doesn't affect me because I am rotating the same way the object is rotating. With alt-az, that is not the case, right? So with alt-az, if you think about it, the telescope or the camera is always in the same orientation. So when it's over here, I'm pointing that way, but when I'm up here, I'm pointing this way. And again, my camera is not rotating. And because of this, you end up with an issue called field rotation, which means you're going to struggle to get long exposures because as you're trying to capture your image and it's moving through the sky, the image with an alt-az will appear to be rotating and you'll get that blur. Right? You won't be able to deal with correcting that blur. So it's not to say that you cannot do astrophotography with an alt-az system. You certainly can. There are a lot of people that do. But just be aware of the limitations. Now there are some mounts that are alt-az mounts that can accept something called a wedge. And a wedge basically is a component that would sit on top of your tripod, between the tripod and the mount, and it would wedge to that particular angle where you're pointing at the North Star for your particular location on Earth. And then your telescope would sit back on that. So you take your alt-az components, sit it on top of the wedge. Now your mount itself, your computerized mount itself, would have to be intelligent enough to know it's on a wedge. Sometimes there's additional firmware you need to load. But just think about that. That's something that you're going to need to do if you want to convert your alt-az mount. Now, I will tell you, most of the cheaper kit telescopes that are out there tend to be alt-az, right? And a lot of people enter the hobby in alt-az. And I think it's just important for you to understand that's fine if you do that. But ideally, you want to find something. If you plan on sticking with this hobby, you want to find something you can eventually convert with a wedge, or just know you're going to have limitations. You're going to have to take shorter exposures. There's just going to be some things you cannot accomplish with that telescope, and that eventually that you may outgrow the mount, or that mount may become your second system, and you may have to purchase another mount or telescope at a later date. So just kind of a heads up on that. So a couple other things about mounts. So there are manual mounts that you can use with handles and just manipulate them. For astrophotography, though, we're going to use computerized mounts, typically called a go-to mount. And with a go-to mount, you can see we've got USB cables, power cables. This will interface either with a hand controller that'll allow you to look for objects and control the system, slew to different points in the night sky. Additionally, they have interfaces, in this case, again, with a USB interface, the ability to connect to a computer. So they have the ability to connect to a computer that can run software. There's a lot of freeware software out there, but we use a technology called ASCOM to communicate with our telescopes and a lot of our telescope-based equipment. And what we'll do is we'll take the feed into a computer, and we can control everything from there. And that's ultimately with astrophotography, how you're going to connect. So typically a go-to telescope and a go-to telescope that has ASCOM capabilities is going to be critical. So we've gotten through the mount itself. It sits on top of the tripod. We talked a little bit about polar alignment at the beginning in this particular case. The one thing I didn't talk about for the alt-az, the polar alignment for equatorial is exactly how you would align the telescope so it can orient itself and you can get great images through the night. With alt-az, the alignment procedure tends to be pointed roughly at north. And then from there, the handheld controller often will take you through a multi-point star alignment. So it'll have you slew to a single star, center it, click a button. It'll say, okay, pick another star, usually in another part of the night sky. We'll go to that star and center that one. And you can stop there with 2. A lot of people find that they get a little more accuracy if they go to a 3rd star, center that one, and then once that procedure's done, the telescope can orient itself, right? It understands, okay, I know where I am because I know where those 3 stars are. So even if I'm not perfectly level, if I'm not perfectly north, it'll figure it out after I do a multi-star alignment. Again, with equatorial, I don't have to go through that procedure. I just simply point this thing north towards the North Star. I fire up my software with my PoleMaster camera, and then I just start making some basic adjustments. It's actually pretty simple to do. I can do it in less than 5 minutes at this point. So now that we're away from that, let's talk about what you would probably call the telescope itself. Here, this is a Celestron 8-inch SCT, Schmidt-Cassegrain telescope. This is an older Nexstar 8i model. It actually came on an alt-az mount originally. I removed it from that and converted it. This uses mirrors to get me the magnification I need. So I have a corrector plate in the front, the light comes in this end, comes down to a big mirror in the back, bounces the image back up to a small central mirror, which then reflects it once again back down the tube, down into my optical train, which we'll talk about here in a minute. So in this particular case, I get to feel like I have a very long telescope because of how we're reflecting it around through the telescope multiple times. So it sort of simulates a much longer optical-based telescope with lenses. However, does it in a smaller form factor. So I personally love the SCT style telescope. There are smaller ones, there are larger ones. The 8-inch, actually, you can see my work, patriotastro.com. I think I'm pretty happy with the imaging I'm getting, and I'm still getting better with it. But there are a number of telescopes out there. There are optical telescopes, refractors, there are other reflectors. You know, there's a lot out there. Just do your research and understand the limitations of your scope. If there are 2 telescopes side by side and one of them is $300 and one of them is $3,000, there is a difference. This is typically not Amazon, where you're just not sure what you're getting and maybe you're getting ripped off. If you go to a reputable telescope dealer, there will be a difference for why the telescope costs so much more. It's probably quality of the optics. It's probably the number of lenses and the types of corrections those lenses are providing. There's a lot of challenges. So know the limitations of your scope. That's not to say you can't start inexpensively. Again, just know the limitations. You're gonna be able to do some things with certain telescopes and not with others. Also understand the magnification and field of view. And your capabilities from that standpoint. Most of the nebula in the night sky are enormous, so you don't need super high magnification. Actually, I end up dialing back the magnification on this telescope to be able to get most of the images that I want to get. Now, if I'm going after a planet, which tends to be very small in comparison, if I'm going after a star cluster, if I'm going after small galaxies, the high magnification is fantastic, right? But if I just want to shoot nebula, things like that, the moon, lower magnification is going to be your friend in that particular case. So again, understand what you're getting yourself into. My guidance there would be to start doing searches For specific objects, go look for galaxy images on Google. And especially if you can go to the links that bring you to something like AstroBin, where people store their astrophotography images. If you go to Reddit, some of the subreddits on there, you can find these wonderful images people are taking, and they put the details inside the description, and the details will tell you a lot about what equipment they're using, and you can get a feel for the capabilities of that telescope and the equipment, the cameras, etc. So do some homework, dig around, and make sure you're getting something you're going to be happy with, right, for the types of images you expect to take. One other thing I want to mention as I get into that, when we talk about the telescope itself, is that I don't even know where my eyepieces are. I stopped using eyepieces a long time ago. If you're getting into the hobby to look with your eyes, you're going to quickly be disappointed from my perspective. Don't get me wrong, there's nothing quite like looking at Jupiter and Jupiter's moons, or Saturn and Saturn's rings, or even the moon up close and seeing all that detail with your eyes for the first time. But there's just a lot of things you can't see with your eye. You can't collect enough light fast enough. So it's important that you understand that you're going to need longer exposures to see some of the things you'd love to see. Your telescope, go-to telescope, you unbox it, set it up, you align it, and you slew to a galaxy. You may see it, you may not see it, depending on the galaxy you're talking about. And again, that all has to do with how much light you can collect in your eye versus on a 5-minute exposure, right? So something else to think about from that perspective. So, telescopes up here, we're not going to go into all the types. Finder scope. So I don't have a finder scope here. Typically a finder scope would be mounted. A finder scope for visual would allow me to look, and it's usually a much wider field of view, so I can find the object, center the object here, assuming these are aligned, and then move over to my primary scope, which has a much smaller magnified field of view. And then I'm close to my target and I can find things. I'm not using that. I'm using some other technology called plate solving for this telescope to just figure out where it is and find everything for me. So in that particular case, I don't need a finder scope. So what I actually use with my SCT here is a laser, and I only use that for things I need a laser for, like planetary. So when I'm super zoomed in, I can see Mars in the night sky. I can use my laser to get me on Mars. And then once I've got that powerful laser pointing at Mars and I can see that I'm pretty aligned, I can jump back over to my computer and start taking some images, right? And get myself to the final stages of alignment. So again, the finder scope or anything that's going to help point you in the right direction would be here. You'll also hear this called a guide scope from time to time, but we're going to talk about that in a little bit here as well. So when you start to look at the telescope itself, or what we call the OTA, the optical tube assembly, when you take that and everything attached to it, I gotta get that connected to my mount. And there's gonna be various hardware to do that. If you buy a kit, it's gonna come pre-assembled, or it's gonna come with all the parts you need. In this particular case, I needed to take my OTA off a different unit and attach it to this particular mount. So what I needed to do is buy mounting hardware. You're going to have to sort of figure that out based on your own needs, but there are different styles. The smaller rails are typically called Vixen or V-style rails. The larger ones are D-style. There are, for different telescopes, ring-based mounts that'll clamp onto the tube itself that then you can mount with a saddle plate or a ring. So there's a lot of different options there. My recommendation would be to use the forums online to see what you need, or simply just call some of the telescope dealers. They can tell you based on your particular mount and your telescope what you need to order, but you're going to need different components to make sure you can get your telescope attached to your mount, because there are some different style connections there that you may need to think about. So just something else there. Okay, so we've got the telescope and everything, we've got it all connected here, right? So the OTA's up. Now we've got all this stuff back here, right, on the back end. And this right here, right, from the front of the telescope all the way to the back of the camera, this whole thing, this is called the optical train. And the optical train is what most people will publish with their images. They'll say, here's the optical train I use, so you can understand I'm taking a bunch of pictures, but here's the optics, and here's all of the filters, and here's everything I used that was in the path of the light from start to finish. So, and that'll start from the front of the telescope all the way back to the camera itself. And here's my imaging camera sitting in the back here, right? So we've got in this case, it's a ZWO ASI 1600 mm, which is a monochrome camera, and it's a monochrome pro, so it's a cooled camera as well. We'll talk about that in a second. Now, when we talk about the imaging train, there's several pieces that could be here depending on what you are doing and what you're imaging. So there are a lot of components. So in this particular case here, right off the back, you may have a visual back if you're going to do visual astronomy or connect different types of components. Here I have a Celestron reducer corrector. So this takes my telescope from f10 down to f6.3. So it'll take my magnification from about 2000 millimeter down to what should be technically around 1280. It ends up being about 1320 in my particular setup right now. So it's a reducer corrector. So it reduces that, but it also corrects, so it flattens my field because of the way the Schmidt-Cassegrain telescope works. You end up with curved mirrors, and it can distort the field of view at the edge. So the reducer corrector is recommended so that we can actually get a flat field of view across the entire image. You don't have any aberrations around the edge of your image. Okay, so you could actually have reducer correctors. You may end up with filter wheels. You may end up with the camera itself, obviously. There's all sorts of things. Spacers, Barlows. Barlows are typically used when you want to get higher magnification. I use it quite a bit when I'm doing planetary astronomy. So with planetary astronomy, you have a Barlow you'll put in the path. It's basically a tube with some optics in the middle that'll either go in double or triple or quadruple or even more to your magnification level. So it's a way to get much higher magnification on much smaller objects. Just know you get what you pay for. Cheap Barlows are not going to give you as good an image as more expensive Barlows. Also, you are going to push the limits of your gear. Don't go buy a 5X Barlow right away. One, it's going to make your field of view so small you're going to be frustrated, not be able to find your target. Two, you're probably going to push your optics past what they can handle in many cases. So with a 5X Barlow, getting that much magnification, you're going to have all sorts of other images that'll be, no pun intended, magnified, right? So any little aberration or something you have within your optics is going to become even more problematic. So start low, 2X, 3X when you're doing planetary, but those are other things that could be in our imaging train. So an important concept we need to cover is backfocus. Backfocus is misunderstood in the industry quite a bit. So backfocus is basically the distance from the back of your telescope to your camera sensor, where if you achieve that exact distance, your manufacturer is telling you that's where you achieve prime focus. That's where you have the best, clearest, flattest image possible. They'll give you this number in inches or in most cases millimeters. And when they say 127 millimeters, they mean 127, not 125. So you, in some cases, have a little leeway. But you will get your best image possible if you do stick to those specific measurements. So it's something that people really are fighting to figure out, how do I get another millimeter here or there? And that's where spacers come in. And there are spacers that are, very long, 20, 30, 50, 60 millimeters in length or more, down to 1 millimeter tiny little spacers. So in this particular case, Celestron tells me that if I'm not using the reducer, the distance from the back of the telescope to my camera sensor, not the camera front edge, but the sensor itself, needs to be 127 millimeters. In the case where I have the actual reducer in there, I believe it's 105, right? So I actually have to meet that from the back of the reducer to the sensor. Make sure you're finding that back focus. So there's a couple things to know. Like on the camera, you have to go to the manufacturer website. And on the manufacturer website for your camera, they'll give you diagrams and tell you how far into the camera your sensor is mounted. That could be 5 millimeters, 6.5, 12, it really depends, right? You'll often hear backfocus with DSLRs. They'll talk about 55 millimeter. Just know the DSLR, backfocus is not a function of the DSLR. Backfocus is a function of the telescope, the optics you're using. When they say a DSLR has 55 millimeters of backfocus, what they're saying is there's a component called a T-ring adapter, and the T-ring adapter is made for your DSLR, and it fits on the front of your DSLR. And that 55 millimeters is from the front of that T adapter to the sensor. So they're just telling you that that 55 millimeters is when you put the T adapter on to connect it to your telescope, that's 55 millimeters to account for, and then you can figure out the rest of your math from there. The DSLR doesn't care what the about the 55 millimeters. It's just sort of an industry standard with the T-ring. Now they do make long and short T-rings. There are other ways to get around that, but a standard T-ring, once attached to your DSLR, is going to give you, that's 55, right from the sensor to the front of that, and now you have to make the rest of your math work, right? So there's a couple things to consider there. Now, when we get to camera types, we have a couple options. You could certainly put a DSLR here or an astrophotography camera. I will tell you that most people graduate from DSLR at the beginning because they have a camera and it saves some cost. They graduate eventually to a dedicated astro camera. So there's a couple reasons for that. They're made for imaging the night sky. They're made for imaging in the dark. Different types of just images than what typical terrestrial photography is looking at. There's different types of color and things you're looking for when you're looking at the night sky, the ability to do much longer exposures. Not to say you can't do it with DSLR. There's tons of YouTube videos of people getting amazing images with DSLRs. But in many cases, you'll find those people that do DSLR for years and then their YouTube channel switches over and then they end up migrating over time to an astronomy camera. So again, in this particular case, this is a cooled camera. So this camera allows me to do long exposures for a couple reasons. One primary reason here is because I can actually cool the sensor chip on this down to, negative 20 degrees Celsius. Why would I want to do that? Well, if you heat up your sensor over time because it's warm, because it's running, because it's electric, you'll actually start to get hot pixels and start to have issues with your images over the night. So keeping it at a consistent temperature and keeping it cooled at a consistent temperature all night long will make your job a lot easier. You'll get much cleaner images of the night sky, especially longer exposures and imaging for much longer, many several hour type sessions. So there's a lot of things to consider there as well. You can also think about the fact that you may want to do color images or monochrome. Most people start in color. Color is considered to be easier. I will tell you that eventually astrophotographers tend, in many cases, to move over to monochrome. Not all of them. I mean, I can make arguments. I go back and forth. I have both cameras. There are times where monochrome just feels like more work from a processing perspective, as opposed to the color images, right? So with a color camera, the light's coming in and I'm grabbing RGB all at the same time, right? So you've got multiple sensors on the sensor chip and they're laid out in a color camera in a Bayer matrix. So it's usually RGB. So you've got basically 4 pixels in a square. You've got a red filtering pixel. It's got a little filter on the front. It's only going to let red photons in. You've got 2 green and then you've got blue, right? Why do we have 2 green? The human eye tends to pick up more green. So RGB is just the way the sensors have been made over time. And there's different Bayering matrices out there. So as light comes in, it's going to hit that area and hopefully the red hits the red, green hit green, blue hits blue, but we're going to suck in all that light over time. And then we're going to have to take this out and then we'll do debayering later to give us the color image that we want. Now we're going to end up taking more color in or more light in to get that image because again, the 4 pixels, the red only takes red, the green only takes green, blue only takes blue. So over the night, we need to make sure we're getting enough of the blue, enough of the red in that particular space so that we can get the images we want. Now with a monochrome camera, it's just degrees of gray. So I'm only going to get black and white pictures, you might think. Well, what we do with that is we put something in front of it here. We're going to actually put a filter wheel in front of my camera. And in this case, this is an automatic filter wheel, right? So it's a mechanical filter wheel. It's USB connected and powered. And inside this filter wheel, I have multiple filters. So I have a luminance filter for light pollution. I have a red, a green, a blue filter. And then I also have hydrogen alpha, sulfur 2, and oxygen 3, which are very narrow field of view, typically for nebula type imaging. So what do we do with that? Well, because this is a monochrome camera that only cares about photons generally, right, as gray, degrees of gray, what'll happen is the light comes in and if my red filter is in place, only the red photons make it through to my image. So I'm going to end up with an image with just the red photons, the red channel. Then I'll take a lot of those, and eventually I'll move on, get the green channel. Then I'll move on and get the blue channel. And I end up with 3 images, red, green, and blue. In many cases, a 4th image, the lume image, right? Which will be just sort of my brightness to give me some detail. So I'll end up with these 4 images, L and RGB. And then in my processing software, I'll take the red, green, and blue channels, I'll normalize them, and then I'll merge them into a single RGB image. So it does take a little bit more work on the processing side, but because the filters are narrow and I'm only capturing exactly what I want, and I'm capturing all the red, every pixel, I don't have that RGB type debayered matrix I have to deal with in a color camera. Every pixel is capturing photons of red. Every pixel will capture green, every pixel will capture blue, hydrogen alpha, and so forth. I can capture all of the images a little bit quicker, right? Get a little bit more detail in a shorter period of time for that channel, right? So there's a lot of arguments. You're making up time on one end, you're losing it on the other processing. But you will see from a detail perspective, most people, most astrophotographers at some point will at least try a monochrome camera, and that's what we're using here today. So that filter wheel that we use is, again, yet another piece that is taking up room in my back focus. So I have to account for the space in the camera to the sensor, and also this filter wheel, and they do make different thickness filter wheels. It's important to understand you get the right filter wheel and the right filters for your filter wheel. There's different sizes, different threadings. Some of them are not threaded. They seat in there. So there's a couple different ways to do this. There are a lot of other pieces you could put in here as well. One of the other things you may see here is I've got this component right here with yet another camera. This is a ZWO ASI 174mm Mini. This particular camera is pointing down into this little component right here. Now, this is called an off-axis guider. So why would I have an off-axis guider? Well, we talked about the fact that I want to take long exposures. Let's say I want to take a 5-minute exposure. Well, my mount should be tracking on that single axis. My EQ mount is tracking on a single axis, and that's fantastic, but it's not perfect, right? It's not going to be perfect. It's probably not perfectly polar aligned. I'm going to need to make some adjustments. So one way to do that is I have this camera here, and it does nothing but lock onto a single star. It locks onto a single star, or in the new version of some of the software, it can do multi-star. But its job is to lock onto a star and look for movement. And if that star drifts in any direction, this camera talks to the computer, which then talks to the mount, and tells the mount to make an adjustment. Move a little bit in this direction, move a tiny bit in this direction. I mean, we're talking about very small movements. But this camera, as a guiding camera, is doing nothing but keeping the entire rig honest, right? So the rig is doing the best, the mount is doing the best it can to keep me aligned, but this camera, the guiding camera, is the one that's actually keeping me so that I can do very long exposures, because it's constantly nudging, right? And if it's very well aligned, it doesn't even have to nudge all that frequently. The goal is for you to align good enough and to have a mount that's accurate enough so that your guide camera doesn't have to work very hard, right? If you have a cheaper setup and you're not properly aligned, you're going to find your guide camera working a little bit harder to keep everything straight, and it's going to limit your exposure time. Right now with this particular setup, I can go well past 5 minutes, 15 minutes plus if I wanted to, with very long exposures. There's some risk reward on long exposures. The longer the exposure, the more likely you're going to run into other issues. Satellites going through your images, airplanes, right? Different things like that. So you're going to find a happy medium of where you think you can get a good image without too much light pollution affecting you, without too many other things affecting you along the way. So it's an off-axis guider because it's not on the same axis as my telescope. More commonly, what you'll find is the finder scope will become your guide scope. So the finder scope that you have mounted here, the camera would go into that. Now it's on axis, right? Because they're both in the same axis, the telescope and the guide camera. And in that particular case, again, that would not take up space in your back focus. You would put spacers here instead to achieve the exact back focus you need. But in that case, we would actually have one guide camera and guide scope pointing in the same exact direction as our telescope. In this case, what we're doing is using a little pick-off prism inside. So some of the light at the edge of the image that I'm not using, that doesn't hit my camera, outside of the field of my camera view, I can pick off some of that, hopefully find a star and then guide based on that. Again, off-axis guiding is going to be pretty common on very long focal length scopes, things like a Schmidt-Cassegrain. Like here, if you're using a refractor, you're very likely going to do on-axis guiding with a guide scope attached. So just make sure that you know about that. Okay, so what else do we have? So we have light coming in, we've got filters changing what is actually hitting our camera sensor, we're guiding, we've got everything set up, the mount is tracking. What about focus, right? So focus can be a challenge. So with focus, you can sit here all night and play with focus. The reality is they do make these units called electronic focusers or autofocusers. So here we have a Pegasus Astro autofocuser. Basically, again, it's powered and USB connected. So from my computer, from inside the house, I can actually refocus if I want, but it can actually autofocus. And I'm not gonna go into a lot of detail, just know what it does is it'll push you out of focus in one direction until the stars get blurry and get bigger. And it'll measure that. We'll just, to simplify it, we'll say it's going to measure sort of the diameter of that big star that's out of focus. And then it's going to move a certain number of steps inward towards focus. Look again, measure that. It's going to keep going and measuring it. Eventually what you'll have is the measurements will start to get to the smallest possible star and then go back up on the other side. And then using trend lines and parabola information, math, right? What it's gonna do is it's gonna say, okay, I had autofocus here, I went to something that looked close to focus, and then I went autofocus, and it's gonna go and find that point in the middle, which should be perfect focus, and it's gonna go back there, take another image and test it. So you can actually use these autofocusers to refocus all night. Why would I wanna refocus all night? Two big reasons. One, every piece of glass in the path is going to change your focus. So every time I change this filter and the filter changes, I take all my red images and now I change to green. Green is gonna focus slightly differently because that glass is different. So because of that, I wanna refocus. The other time you're gonna refocus, not just on a filter change, but over the night, the temperature drops. And because we're pointing at the night sky, through the law of thermodynamics, you're actually gonna start venting heat. You're gonna lose heat to the surrounding area. And optics change, the tube changes, there's a lot of things that'll change as the temperature drops. So your telescope will contract. I mean, obviously it won't be perceptible to the eye, but it'll be enough to change the optics. I mean, we're talking about millimeters here, right? So even throughout the evening, what you'll do on the temperature change is you'll telescope to monitor that HFR, that width of the star throughout the evening. And if it changes by a certain amount, go ahead and refocus, right? So the system can automatically do that. And again, that's the power of an automatic focuser. So now we're automatically focusing, we're guiding and staying on target. Our mount is centered and doing its job. The camera is taking image after image after image. The filter wheel is automatically changing based on our target definition. So it's automatically taking so many red exposures and so many green exposures and blue exposures. So everything's sort of automated. So what else do we need to think about here? Well, one other couple pieces you might see on here. One is these straps. What are these straps all about? Well, we have another problem with our telescopes because we image at night is with the temperature changes, we can get close to the dew point. And with the dew point, the telescope can start to get dew on the lens, on various lenses. And if we have dew on the lenses, the problem we're gonna run into with dew on the lenses is that obviously our images are done at that point. Once we get dew on the lens, it's wet. There's just no more imaging you can do. And why does this happen? Well, it happens because we're pointing at the night sky, and the night sky is cold, and our telescope probably started a little bit warmer or is, at ambient temperature at some point, but we are, through the law of thermodynamics, we're gonna lose our heat to the coldest area, so we're gonna start venting out that tube up into the night sky. So a couple things we can do. One, we can heat it up, right? So we have these little heater straps here, and there's actually a heater component back on this side. It's basically sort of a tiny electric blanket for your telescope optics. So I've got two on here. You don't need to necessarily. You can get small ones for different lenses, different size lenses, different points of your optical train. But I've got two large ones up here, and I just turn them up to a certain amount, and it just runs a low current through that to warm the front of the optics. so that it doesn't ever drop to the point where I hit the dew point and have that issue, right? The second thing we do is we can put a dew shield on the front, and this is more common, right? So not everybody will use heat straps, but you can use a dew shield. And the way the dew shields work, we'll see if we can actually get this up here, and I'm not gonna put it on correctly, but you'd put a dew shield on the front and it would be aimed correctly, but you'd put a dew shield on the front. So this does a couple things for you. One, blocks a lot of ambient light that's in your surroundings. So a dew shield can be very helpful from that perspective. Secondly, as we're pointing at the night sky, law of thermodynamics, what does this do? We're venting through our optics up towards the night sky. By putting a dew shield, we're saying that you can only vent up that small sort of chimney of area that the dew shield creates, rather than in any direction. So we're limiting how quickly we lose our heat. Believe it or not, it actually will work. Now, a dew shield itself is not going to solve your dew problem. It's going to delay your dew problem, or it may solve it long enough for you to image everything you want to image. A heat strap will keep it at the right temperature so that you don't hit that dew issue. But again, a dew shield is very common. Some telescopes have them built in. You can buy them. I actually made this one out of a piece of exercise mat that I cut to shape. And I've got some different lengths here. If it's a little bit breezy out, I pull out the smaller dew shield so that I still get some of the assistance, some of the light blocking. But again, it's not a big sail. It doesn't cause me all those problems that you might have with a much bigger dew shield. So think about dew as another issue you're going to run into. Last couple things. Power. Most of our gear is going to be 12 volt powered. I'm going to do another video on how I run 12 volt powered. The 12 volt power that's going to come out is usually going to be a power brick that converts it to 110 or 220. Depending on where you are in the world. However, sometimes they will just give you with your gear those cigarette lighter adapter 12 volt native DC connections that you're going to need to convert. So you may need to buy a converter brick that'll go from 12 volt DC with a cigarette lighter adapter connector that you can plug into your wall socket or to an extension cord. But they make it all 12 volt DC because while you may run it at home off AC power using the power bricks, you may also probably want to take this to a dark site somewhere in the field where you're not going to be around power. And in that particular case, you want to run it off a battery, typical car style battery, 12 volt battery. So I'm going to do a video on that as well. So I'm going to show you in another video how, if you want to, you can convert all of your 12 volt cabling to smaller cabling, get rid of all those power bricks, make it native 12 volt DC, and then run it all back to a single 12 volt DC power supply that'll convert to 110. So get rid of all those power bricks. Also, what that'll allow you to do is seamlessly take your rig and move to the field and plug into a battery box, which I'll show you how to build soon as well. So that again, we can get rid of all those power bricks. We have no reliance on 110 or 220 power, AC power. We can go native DC. You're also going to have, for computerized components, a lot of USB 2, a lot of USB 3. Some of the cameras actually have USB hubs built into it. I've actually got another USB hub mounted on the other side because you want to run your USB cables. Everything that needs to communicate with the computer. So your filter wheel, your cameras, right? So I've got 1, 2, 3 cameras, right? My main imaging camera, my guide camera, and my polar alignment camera are all USB. My mount is USB. My filter wheel is USB. My autofocuser is USB. So I've got a lot of USB that I've got to get back. Now, some of it does connect here to the back of my camera, which happens to have 2 extra USB ports on it. And then the rest of it is going to run back to my USB and then off to a computer. I've actually got a computer down here you can't see. That computer's got Wi-Fi on it. I run it outside. I got it inside a little bit of a case. And then from inside, I just remote control the entire rig from there. So, you know, the last thing I want to leave you with is just one other keyword that you may want to do some research on, and it's plate solving. And I'm only going to mention it because it's the other piece of the puzzle that makes the EQ mount and the computer setup work so that I can literally program it and go to bed for the night and then come out in the morning and just roll it back in the house. So what plate solving is if you have ever used any of the software packages on your phone to figure out what a a song is, right? So we have music's playing and you say, hey, what's this song? And it listens to it. It listens to a small sample of the song, sends it to the internet and says, hey, look through the database and match this up. And it tells you exactly what song you're listening to. And it's pretty amazing technology. Plate solving is fundamentally the same thing, but for the night sky. So when we polar align, we're giving the mount a good idea of where we are, right? It's got some coordinates and it also knows that it should be pointing roughly in the right place, but it still is not going to find everything perfectly. So what do? Well, what we do with plate solving, because I'm connected to a computer, is I can tell the telescope to go find a galaxy. So I say, go find Andromeda. It points to where it thinks Andromeda is and it takes a picture. It sends that picture to a plate solving software package. And it basically says, hey, here's all the stars and here's the layout. Where am I in the night sky? The plate solving software very quickly runs it through its database and says, oh, you're actually pointing here. You're not pointing exactly where you want to be. Let me move you. It talks to my telescope. It tells my telescope to move, takes another picture, compares that picture. If it's still not perfect, I mean perfectly centered, within some degree of tolerance, it will actually take another picture again, right? Look at that and then recenter it. So it'll tell my mount to move and eventually it'll be perfectly centered. So plate solving makes all of this automation come together without the handheld controller, right? So the handheld controller you're typically going to get with maybe most of your mounts that are out there are going to try to find the object and get pretty close, but then you're often going to have to search around a little bit to find it. It won't be perfectly centered. Plate solving ensures that because everything is connected to the computer, when I say I want to see an object, I guarantee I'm going to see that object, right? It's going to point me right to it. So just something else to consider and something else you may want to research. We'll probably do something about that later as well. So again, I know this was a long video. Hopefully you found it somewhat helpful. There's a lot to consider when you think you want to get into this hobby. Do think about the fact that most people get into the hobby thinking they're going to see things with their eyes and they're going to use, optics, and you certainly can do that, but you're going to tend to outgrow that pretty quickly unless you really love the moon. For the most part, most of the things you want to see, most of the nebula you want to see, the Horsehead Nebula and all of those other galaxies, they're going to be either extremely faint or impossible to see with the human eye. A lot of the wavelengths of the light that you're going to get and the amount of light and the exposure length you're going to need, you're just not going to get there, right? So if you do want to get into telescopes, if you want to get into astrophotography, certainly consider an equatorial mount or at least something with a wedge. Start with your DSLR. Just start taking pictures, right? So there's plenty of videos out there, people pointing you in the right direction to just get into it and see if it even interests you. There's a lot of frustration in this hobby. You have to have a lot of patience. And you have to be willing to stand out in the cold for long periods of time to get things to work. So hopefully you enjoyed this video. Again, for the beginners out there, if you have questions, leave them in the comments. Please subscribe. I'd love for you to check out some of my other videos, some of my solar photography, my asteroid hunting. There's a lot of different things that I'll be sharing with you in the future here as I get started and keep moving forward. And I hope to see you again someday soon.